Hey guys, this is Mr. Brengle, and today I'm going to go over FPM worksheet number 2. You're going to notice that I've already written in some of the answers here. That's just in the interest of time, but I'm still going to talk through everything. So number 1, explain what a normal force is and give an example. So a normal force is a contact force that is exerted by a surface onto some object, and it is exerted perpendicular to the surface. So that does not matter whether you're on a level surface or an incline. It's always perpendicular, meaning a 90-degree angle to the surface that you're on. The example that I have here is a box on a table. So I'm going to draw the table, and here is the box. And the normal force would be going up through the box, perpendicular to the surface of the table here. So there would be a right angle right there. Now, if the object was on an incline and we put the box right here, our normal force would be going up this way, perpendicular to the surface and through the box. Looking at number 2 here, can an inanimate object such as a table exert a force? Well, yes, we just showed that in the last example. A table can exert a normal force on an object. Can the magnitude of the force exerted by an inanimate object change? Explain and give an example. So again, yes, we could add another box onto the table, and then the normal force would have to change, because if it didn't, then the boxes would fall through the table. So as long as the table's sturdy enough to hold the boxes, the normal force will increase as you add things onto the table. So draw another little example here. We've got our table, and this time, we've got the first box here, and then we go ahead and we add on a second one on top of it. So that adds extra weight, right? So our value for Fg here, the combined weight of the boxes, has changed. It's increased since we added an extra box. So that means that the normal force that opposes the downward force of the weight of the boxes would also have to increase. Number 3. If the acceleration of an object is 0, are no forces acting on it? Explain. So this depends. You have to remember that acceleration is caused by a net force. Remember, F net is equal to mass times acceleration, and that rearranges to acceleration is equal to the net force over the mass. So you have to have a net force to get acceleration. If there's no acceleration, that could mean that there are no forces acting on the object, but it could also mean that there are forces that are balanced on the object. And we've done a lot of examples in class, like something traveling at a constant velocity. So let's say it's traveling to the right at a constant velocity. And I'm just going to look at the x direction forces here. You could have something like the force of thrust is propelling the object, and then the force of friction opposes it. And as long as these two are equal, then the object will move at a constant velocity. That would be an example where the acceleration is 0, but there are still forces acting on it. Okay. To get, maybe we have a baseball in outer space and we throw it in outer space, and it's going to continue on at a constant velocity forever until it hits something, until a force acts on it. And so that would be an example where the object has no acceleration and there are no forces acting on it as it travels through space. Go ahead and move to number 4 here. Number 4 pertains to this picture right here. It says, how does the force block A exerts on block B compared to the force block B exerts on block A? So this is Newton's third law, right? Every action force has a reaction force that's equal and opposite. So the force that A is exerting on B is equal and opposite to the force that B exerts on A. And if they weren't equal, what would happen? Well, wherever there was a net force, those objects would be traveling in that direction. They would accelerate in the direction of the net force. Since they're not moving, they have to be equal and opposite. So now this is asking us to draw and label a quantitative force diagram for each block. So we're going to do block A right here. Okay. As always, we have the force due to gravity that's acting on block A by the Earth. And then the force that opposes that, it has to be equal here because A is not moving vertically. This would be the normal force that's acting on block A from block B. Now we'll switch over here to block B. So this is where we're going to have to start adding in extra vectors, okay? And I don't want you to combine them into one line. So there are two forces acting on object B. You've got the weight of object B, or the force due to gravity that's on B by the Earth. But then there's also that force of A on B here. So this would be a normal force because it's a contact force. And this would be on box B by object A, or box A. So the reason I drew the normal force larger than the force due to gravity is because box A is more massive, meaning that it has a greater mass and therefore a greater weight than object B. So object B is not moving down, so there has to be some force that's opposing these two here. And this is not going to be to scale. These lines are not going to be to scale, but we're still going to use our equivalency lines. This would be another normal force that is acting on object B by the table. Now, to show that all of this is equal, I want you guys to put a dash here and then just put a dash through these two lines right there. That tells me that the sum of the forces that are pointed down are equal to the sum of the force that's pointing up. On both of these situations here, the sum of the forces in the y direction is equal to 0. And the sum of the forces in the x direction would also be equal to 0 because we have no forces in the x direction. All right, let's move on to page 2. All right, so number 5 says, how does the force that block A exerts on block B compared to the force that block B exerts on block A? This time, they're moving at a constant velocity because of some push force that's moving them to the left. So does that change anything? No, the force that A exerts on B is equal and opposite to the force that B exerts on A because of Newton's third law. So what will change here would be the force diagrams. We'll do object A right here. Okay, so let's start with the forces that we know for sure, which would be the force due to gravity on block A by the Earth, and then the normal force that's on block A by the table. And just sometimes people get confused because A isn't on the left here, but we are doing this force diagram first. So these must be equal. Okay, and then I'll change colors here for the x direction. So we have a force that's pushing to the left on object A. This you could call a normal force. It is a contact force, or if you want to call it F push, that's fine. So I'll put Fn or F push. Okay, and this would be acting on object A by the finger. All right, now we've got to think about the forces that are preventing A from moving or opposing A's motion. And there are two of them here. The first one that we have would be another normal force, which would be the force exerted on object A by box B. So they're in contact. B is pushing back on A. We just answered that in the last question, so that has to be there. The other force that would oppose its motion here would be the force of friction, which would be acting on A from the table. Okay. Now, it does say that the object is moving at a constant velocity, so that means that this force has to be equal to the combination of those two forces. The sum of the forces to the right is equal to the sum of the forces to the left. So, for object A, sum of the forces in the y direction is equal to 0, and the sum of the forces in the x direction is equal to 0. Everything is balanced. So now, let's look here at object B. Okay, so B. And again, we'll start with the things that we know for sure. So the force due to gravity, which is acting on B by the Earth, and of course the normal force that opposes that, which is acting on box B by the table. These must be equal. So right now, if we wanted to, we could just come over here and say, all right, well, the sum of the forces in the y direction is equal to 0 because those two things are balanced. So now let's look at the forces in the x direction. So let's start to the left. What is pushing B? Because B is moving to the left. There's some force acting on it. This would be a normal force because there is a contact force between A and B. So this would be on object B by object A. And then what's opposing the motion of B? Well, unlike object A, there is no other box in front of B or to the left of B. So the only thing that's opposing the motion of B would be the force due to friction. This would be acting on object B by the table. These would need to be equal here. We'll use double hash on that one. So, and we would say that the sum of the forces in the x direction are equal to 0. Once again, because it's moving at a constant velocity. If it were accelerating, then the sum of the forces would not be 0. Okay, so now we're looking at another situation here, which is the same boxes as the last problem, but now they are being pushed from the left to the right, and they are at a constant acceleration. Okay. Now, how does the force block A exerts on block B compared to the force that block B exerts on block A? Well, this is where some people get a little confused. The answer is still that they are equal and opposite, even though the objects are accelerating. The key here is to just think about Newton's third law. You have to understand that every action force has an equal and opposite reaction force. So the fact that the objects together are accelerating doesn't really have anything to do with the action-reaction force because there are a bunch of other forces that we're neglecting to consider. This question is just asking about what force does A exert on B and what force does B exert on A. So to figure out why it's accelerating, we need to do some more force diagrams here. I'm going to give myself a little more room. Okay, so let's again start with object. Let's start with object A here. So, as always, we have Fg, which is acting on object A by the Earth. And we have the normal force which opposes that, which is acting on object A by the table. These are equal, which means that the sum of the forces in the y direction are equal to 0. Now, since object A is accelerating to the right, that tells us that we do have to have a net force to the right. So we could just go ahead and draw these lines on here and show that this force to the right is larger than the force to the left. Okay, now we just have to figure out what that is. Well, the force that's pushing A to the right would be a normal force because it's in contact with B. So this would be on object A by object B. And then on the left side, opposing the box A's motion would be the force of friction, which is acting on object A by the table. And that's it. And that shows us right there that object A is accelerating because we have a net force in the x direction. Now, if I say that to the right is positive, which I would because the object is moving to the right, then this would be equal to positive mass times acceleration. Okay? Just remember, a net force causes acceleration. All right, let's move over here to object B. Once again, we've got the force due to gravity acting on object B by the Earth. And we have the normal force opposing that, which is acting on object B by the table. These must be equal, which means that the sum of the forces in the y direction is equal to 0. And they must be equal because object B is not moving up or down. Kind of have left that out, but just to clarify. Now, again, object B is accelerating to the right, so we do have to show that whatever is going to the right is greater than the forces to the left. Now we have to be careful here because while there's only one force going to the right, which would be your, again, you could call this normal force or you could call this F push. Okay, this would be on object B by the finger. We've only got one force going to the right. However, there are two forces that are opposing object B's motion. That would be your normal force, which is acting on object B by object A. And on top of that, you have your force due to friction, which is acting on object B by the table. Now, I don't really care which of those arrows is larger. We really have no way of determining whether the normal force is greater than the force of friction. What's important here is that you show me that this force on the right is greater than the forces on the left. Okay? Now, again, this is not drawn to scale, right? That arrow on the right is about the same size as the normal force going to the left. Use those hash marks to make sure that I understand which is larger.